this won't be the official start of the lecture. I'm just talking. So this slide is related to the hard exercise I'm going to assign at the end. And I'll explain the slide in more detail as we go along. But I forgot to put this exercise on. It's very cool. It's a more conceptual exercise, and you'll get to see it near the end. But how many of you have heard of, seen something like these dependent records that I put up there? Pretty cool type, right? I mean, this is part of object-oriented programming, and these records aren't ordinary ones. They're dependent. The second component can depend on the first and so forth. So the amazingly cool thing about intersection types, which will be the topic of the lecture, is that in 2003, Alexei Kopylov showed how to build those dependent records out of a single intersection of singleton records. It's like an unbelievable thing. And when he discovered that, we rebuilt the whole New Perl library, which we could do automatically to use this type. That gives you a measure of significance of a discovery by a graduate student. I mean, this was an amazing, amazing discovery that caused us to change how we did everything. We used to use just tuples. But the neat thing about the New Perl system is that you can rebuild the theory. So we said, okay, we're going to replace this, and we did it pretty automatically. Anyway, I hope that'll motivate you to look at this hard problem. But now's the lecture starting. Zaina wanted me to wait 5 minutes, but I saw a lot of you were wondering, what are you doing standing up there? So that's what I was doing. So here's where we ended up last time. I didn't get through anywhere near as much of the completeness theorem as I wanted, so we're going to continue with that. And the plan will be, first, do you have any questions about what we did so far? Because what I plan to do is look more closely at this completeness theorem. Because one of the nice things about it, not only does it solve a long-standing problem in constructive logic, but the procedure that we came up with you can use. You guys could actually play with this. Take an evidence term and turn it into a proof. There's an algorithm, which we've written in New Perl, that does this, and I checked most of the examples with this algorithm. And I'm going to end this lecture with a really interesting challenge problem that I tried just before I left to see whether New Perl would do this in a beautiful way, and it did. So you're going to be in a competition with the system to see if you can produce a really beautiful proof from the realizer I show you at the end of the lecture. But before you can do that, I have to tell you, how does this completeness theorem work? Right? So it has this constructive character. It says, if you show me in type theory why, or if you just tell me, you have to believe it. So you find a realizer. You say, I know this guy is evidence for the truth of this formula. It's constructive evidence. And you tell me this. You don't have to give me a proof. You just say, trust me. We then run our procedure on it, and if you were right, out will come a proof. If you were wrong, it might just sit there grinding away forever. And that's okay with you, right? Because you can say, well, New Perl must be slow, it'll eventually get there. And if we're really pressed about this, we'll say, well, could you actually prove to us that you've got a realizer? Okay, so what I'm going to do is take the problem. Well, I'll use one of those exercises. Let's see, the one I'm going to use, where is it? Well, okay, we'll get to it. But did people, by and large, get the exercises that I assigned? I know a number of you did. And so how many people feel comfortable that they can build realizers now? Whoa, oh, come on, there are more of you. I talked to more of you than that. All right, well, okay, I hope you get a little more comfortable because this, well, for computer scientists anyway, what is this? It's showing your programming prowess because I give you a first order formula, and that's a specification in intuitionistic first order logic of a programming problem. That's what it is. Okay, here's a programming problem. So if you're a hotshot hacker, you should be able to look at that and say, yeah, here's the program. Just write it down. It's only first order logic, no data types. The data type is a domain D, abstract domain. You don't know anything about it. Okay, so anyway, let's get on and see if you can get there. But one thing to notice already about what I explained from analyzing the proof terms is that we have a very nice constructive consistency proof for first order logic. Because what did we do? We showed that if something is provable, we could actually, from the proof, build the semantic realizer. All right? So we know that all the provable formulas are true. And the technique of program extraction is actually, can be seen then as a consistency proof, a constructive consistency proof. And I think that's pretty cool already. So we have that result. The other thing to notice, Laurent was one of the people who said we should emphasize this, is we also get a proof of cut elimination for first order logic. It just comes out because the cut proof gives you evidence, and from that evidence you build something without the cut. So you've got a free proof here of a pretty hard theorem. If you look at it only proof theoretically, Gensen got his name attached to it, so the cut elimination theorem can be subsumed in the completeness result, which is pretty nice. Okay, and the other thing you can notice that we're doing is we're building a constructive model theory, or an intuitionistic model theory, which is nicely tied to the proof theory. And yet it's somewhat more abstract, I think. Those realizers were easier for you to grasp, I think, than the proof rules. So those are some of the things we're up to. Okay, but let's now try to formulate the completeness theorem and then go through the key steps of why it's true. So remember, what we've got, the starting point for you, I think, is to notice that those simple proof rules generate uniform or polymorphic, we don't have to use the word uniform yet, all the realizers that we get from the proof, except for P or not P, are uniform, that is, are polymorphic. They don't mention the atomic formulas in the formula that they realize. So I hope you get that point. That's a really key thing that's not true in the classical proofs. So the classical completeness proof of Gödel isn't polymorphic because it uses P or not P, and those atomic propositions get threaded through the classical realizers. And that makes them a very different kind of realizer. So yes, indeed, you can say, okay, you can provide a realizability semantics also for classical logic. That's, I think, a nice observation. But those realizers are not polymorphic realizers. Okay, so one idea then, once you see this point, and how many are comfortable with this? If you come away with only one thing from my lectures, I hope that's something you'll understand, that from a proof in intuitionistic first order logic, you can extract a polymorphic realizer. So how many people think you could tell that to your mother when you get home? Okay, how about to your office mate? All right, good, because I think it's a key point, and it's the starting point for understanding the completeness theorem, because what we would like to have for completeness is some kind of if and only if result, right? Something is provable if and only if it's polymorphically true. So that's going to be our conjecture, because that's what you'd expect from a completeness theorem. It better capture what's true about the proof rules. Okay, so let's see if we can do that. And if we do, as I said, we're going to then have a constructive way of going from the evidence to the proof. So how can we make this idea precise? How did Mark and I get to it? Well, this is the advantage of reading a lot about these basic problems. So already, as soon as you see this semantics, propositions as types, proofs as programs, the natural question is there a completeness theorem for it? That was, as I say, Bett formed that question in 1947, and people were taking cracks at it all along. And Lauchley, in 1970, wrote a paper that I thought was it. You know, I thought he really had it, but his proof was classical. But he had the idea of uniformity. He thought the only thing missing from Bett's approach was somehow that he didn't use the term realizer yet. He said somehow the evidence has to be uniform. And I don't know how he got that intuition. He doesn't say. But he translated that into the idea of permutations on the domain. That's the way a mathematician would think about uniformity. It shouldn't matter what the domain elements are. So he defined these permutations of the domain, and he showed that what he called the proof terms were invariant under these mappings. And so he then was able to prove a classical theorem based on that idea. And since that time, a number of computer scientists tried to generalize this. One of my former students, Mike O'Donnell, spent many years trying to generalize Lauchley's result. So we knew about this, and we were wondering, okay, is there another way to get uniformity? And so what does that uniformity mean? So it means to say no matter what domain we pick, so whatever type is the domain of discourse D, and no matter what atomic propositions we're given, the realizer for the formula will be the same. It'll be invariant under our choice of domain and the meaning of those atomic propositions. So, for example, if you were trying to characterize the equality predicate, our theorem doesn't have a built-in equality predicate, right? So you might say, well, I want my domain to have equality in it. So one way you could do that is to just introduce a new predicate called EQ of x and y, and axiomatize it by the three standard axioms. Make sure it's reflexive, transitive, and symmetric. So you write down those axioms. But if that's all you do, that's fine. We can subsume the result in our completeness theorem, because you just add those axioms to any hypothesis and you're all set. As long as you keep that predicate, that EQ predicate, kind of abstract. You don't care what predicate it is, as long as it satisfies the axioms, okay? The other thing you could do with equality is build it in. You bake it in there and say this predicate must be the equality on the domain. Now, if you do that, it's not going to be uniform, right? It now will depend on your equality. So that's a way to contrast a polymorphic choice of R versus one where you say, hey, I know what it is. It's equality. We're not going to know what those predicates are, and that's what we're thinking for first-order logic. It's an abstract domain. And what we discovered, because of the work of people like Kopelov, who in 1990 or so had shown us that intersection is powerful, because of the work of Capo and Dazzani showing these really cool uses of intersection as a logical operator, because of the work of Reynolds and Pierce, we knew intersection was a very important thing, and it just occurred to us like, wow, yeah, if we just used an intersection quantifier we could actually capture uniformity. Let me just, as an aside, about these results on intersection have always been sort of dramatic in the beginning. So when Capo and Dazzani introduced just binary intersection, you intersect two propositions, A and B, they gave this wonderful interpretation of it. They said, okay, something is in the intersection of A and B if you've got the same proof for A as you have for B. So this was a cool idea. Use the same proof. Yes?
I have a really basic question. I realize they're using proof term, right?
Yes, but I don't like to use that term because it's not. So let's deal with that because I think this causes a lot of confusion because the proof term, which is what De Bruyne liked to call it, it has much more information than those realizers, right? It's got the tree structure there, for example. You've listed out, okay, here's how everything hangs together. And certain order properties have to be maintained, right? I've got this order of the hypotheses and so forth. So it's not really a proof term in that sense. We've blurred some of those distinctions. It's more abstract, for example.
Okay. And so completeness, by completeness, you by writing down a term, then every term, then that term is improved for every proposition that corresponds to a type that needs to be found.
Yeah. So I go the other way. I'd start with formula. So you've got a formula for it, so you know why it's true. You found a program. You've seen that this spec can be programmed, and you wrote the program. That'd be a nice term for it. Well, it can also be a data type. So it's either a data type or a program. So you found it, and you say, now I know this thing is true constructively. That's what I know. And we're going to say, okay, if you've got one of those, we'll give you a procedure that will allow you to reconstruct the proof. And that should seem very plausible from the simple examples I've shown you so far, right? Because the ones you guys created, the simple ones I gave you, you can sort of see the proof in there. And now you're going to wonder, well, why is this hard? You know, maybe you think you already have it. You get the idea. But you're going to see that it doesn't, and that's what I thought, by the way. When I saw this, I went running into Mark saying, wow, isn't this great? And he said, well, yeah, show me how you do this. Oh, okay, I do this. Well, then what about that? And it started to get harder and harder and harder. It took us, I don't know, too long to figure it out. So I'm going to show you all these hard steps. But it won't take a year. It's going to take a few. Yeah, okay, that was a very good question. So, others like that? Yes? Yeah, so that's what I've been trying to get at. And that's a hard idea here, but we're going to use these quantifiers. I'm trying to give that idea already with the intersection, say, of two propositions, A and B. Capo and Dazzani said, okay, the meaning of, the logical meaning of A intersect B is that the things that type, that intersection type, have to be in both A and B. So they're proofs of A and they're proofs of B. And that shows you a kind of uniformity, right? It's like you can't tell A and B apart. And we're going to do this for everything. The way we're going to get uniformity is we'll quantify using a more general intersection. I'm going to show you that. Like in 5 minutes, if you don't have the idea, we'll keep at it. Because that is the key notion. What is uniformity? But the intuitive idea is like what I said with equality. It can't matter. The truth of the proposition can't depend on what particular one you picked, what particular atomic proposition you picked, like for this equality. You don't have to actually look at the domain and know what is equality on that domain you picked. And you can't know that because I can pick any domain. In this semantics, as long as I give you a type, the thing should work uniformly no matter what the type is. So the truth isn't going to depend on whether I gave you integers or lists or strings or trees. The truth will be independent of what that domain is. Okay? Yeah.
So would another word for already be parametricity?
Yes.
Okay.
Yep, that's another good word for it. I use uniformity because it's what people started calling those quantifiers and so on. But that's a very good word for it as well. Okay, so we'll keep working on this idea. I don't expect people to. We had like 7 years to live with this idea. It took a long time for us to digest it. But a cool thing, by the way, when you think about that intersection type, that binary intersection, the typing problem goes from being linear time to type terms that just have and, or, not, and implies to undecidable when you add the intersection type. That's like an amazing result, right? The complexity goes from linear time to undecidable. So when I was explaining this to Juris Hartmanis the other week, he pointed out to me that the same kind of thing happened in formal language theory. When you added intersection to context-free languages, all of a sudden you got undecidability. So there's something fundamental going on here. All right, so anyway, we at least now have the words to state the theorem, and we'll try to make those words sensible. So the theorem, the corollary is the thing we're after. A formula G of intuitionistic first-order logic is provable if and only if it's uniformly valid. That's our theorem from 2010. You'll see why we need that, why we get that as a corollary, and we have to go to something called minimal logic. And I already told you what the minimal logic is. It's the logic that takes out the rule that says from false you can prove anything. And you guys have used that rule already a couple times in examples. That's called ex falso libet. From false, anything follows. You take that rule out and you replace the primitive proposition false by an arbitrary named constant, which we're going to call any. That's what I used in the first lecture. So that's any designated proposition, but it can be either true or false. You can assign it either way, but it's a constant that you've named. And by the way, in the Kripke semantics, they do the same thing over there. It's pretty interesting that in Kripke semantics, they invented fairly late in the game, Feldman invented these exploding Kripke models, is what they call them. Those are models in which in which false can be interpreted as true. And what did they do? They were really going for this minimal logic. They said, yeah, we can't let false really be false. So some nodes in the Kripke world, they say explode, because false can turn into anything, including true. And you'll see why we need that in a few minutes. But minimal logic has been around for a long time. And in fact, Helmut Schwichtenberg and Ulrich Berger and Monika Sensenbrenner built a very nice system called MinLog based on minimal logic. That's a wonderful theorem prover, which we won't have time to talk about. Okay, so here's how we're going to get at uniformity now. We're going to use this intersection type. This is the Capodesani one, the binary intersection type. And remember, what's in that type, A intersect B? These are the elements that are in both types simultaneously in A and B. So they're proofs that prove both A and prove both B. Now, how could you have such a thing? Well, if you start with atomic propositions, say, and for the atomic propositions, the only evidence we allow for them is either some token that says the atomic thing is true, because we don't know enough about the structure of it to say why it's true, or nothing, the empty type. So what this is saying for the atomic propositions is pretty straightforward. Any two of the atomic propositions, if they're true, they're going to have the same trivial element in them. But the real power of the intersection type comes when you do an intersection over a family of types. So here, up at the top, we've got a family indexed by a type A. So we pick any type A. For every element in A, we have another type. That collection is called the family. And we can now take an intersection there, and we'll say the elements that belong to that big intersection type are all the things that belong to every one of those B sub A's, right? So they're in all of them. So that does act like a universal quantifier. You're really saying here for all of these propositions B of A, all of those B of A are true. And in fact, they're proved the same way. They're proved uniformly. So here's an example. At the bottom there, we have, we're quantifying now here over the set of types of the first level, types of 1. And we're saying, okay, show me all the proofs of A implies A for any proposition A. And you might think, well, there's nothing in there. In the Koch type system, there wouldn't be anything in that intersection because they don't have polymorphic realizers. But in an extensional type theory, you get lambda x dot x in there, and you get all the other elements that are in there are equivalent to that lambda x dot x. So this starts to give you an idea of uniformity, right? Maybe you don't get the whole picture yet, but there's a pretty good piece of it, I think. So the way we write that universal quantifier now is with a for all sign with brackets around the little a in capital A. But I want to remind you that it's intersection, so I'm not going to write it that way. And to tell you how important this type is, again, as a measure of things, we started to, and maybe this example is really going to, maybe this is the example I should have put on the slide. Think about this quantification. If we wrote this out as a piece of logic in Koch, the quantifier would be here for all A of type, of say the first level of the set type, A implies A. So you could write that as a quantified formula. Now that's not uniform, but that's quantifying over these types. So there you see the relationship between the universal quantifier and this thing, because in Koch it will be true that for every type A, A implies A. But there'll be different proofs depending on the type, right? You give me the type of natural numbers, then I'm going to get a function from natural numbers to natural numbers. If you give me the type of binary trees, you'll get a different identity function. Yep. Yeah, that's in predicative. This is a predicative one over that first universe. So that's a key thing. It's a predicative quantification. Now, when we noticed this universal quantifier was handy, what we saw is that we could make our realizers much more by taking all the quantifiers, the leading quantifiers that said for every type in type 1 or every type in type level 2, we could strip all those quantifiers out and replace them by one intersection type, and then in the realizer, a whole bunch of lambdas. All the lambdas for those type objects would disappear. And Mark was so happy about this. He said, look, we're shrinking the size of most of our realizers by 2 or 3%, that he decided to install this quantifier on the existing base of all of our theorems. He said, I'm going to take every theorem that starts with quantifiers for all types, and I'm going to put a copy of it right underneath that theorem that uses the intersection type, and I'll change the tactic that we use for proving that a type is well formed in just this one place. And he said, let's see what happens. How many new theorems do we get? So he ran through the whole library. I think he got 500 new theorems. And then he ran this tactic. And as I recall, he proved like 250 of them totally automatically. Had to tweak the tactic a few more times, then ran it again. And he was so happy, he said, well, it took me about an hour, and I added 500 new theorems to NuPerl. They're all in there. And this simplifies all of our realizers, takes all those stupid universal quantifiers out. So that, again, is a sign that you're on to a type that's really important. If you decide you're going to change your whole library, like we did for Kopolov's type, well, you're really betting on it. So we bet a lot on this type. Okay, so here's the conjecture that we said. A formula is provable. Yeah.
Between your term and Cork is that in the case of Cork you have lambda A of type, lambda X of A, X, and here you have just the Curry style version.
Yeah. Yeah, the realizer is a Curry style thing.
So does this also mean that these intersection types only make sense in a Curry style system?
In a polymorphic system, yeah, you can't put the types on the...
So you need okay, so in a Church style system with type annotations, intersection types are out of the way. Right. Okay, all right.
Okay, so conjecture then. We have this conjecture. A formula G is provable if and only if it's uniformly true with respect to the domain and all of the atomic propositions Ri. So let's take this example that you guys did. How many of you got this little exercise? Oh, again, I swear. Okay, good, good. All right, so there was something really cute about this that many of you noticed right away. Robert noticed it immediately. Let's see how it comes out. What we're going to do is take the evidence term that I'll explain in a minute for this thing, and then we'll use it to build the proof. And this will be the completeness theorem in action. And also it's doing a dual purpose. I'm explaining an answer to the question. Okay, so here's how you should have all gotten started anyway. You say, well, look at the structure of this thing. It's an implication. A big conjunction implies a disjunction. So you're going to have a hypothesis here, lambda h, to start. Because every realizer for an implication is a lambda term. So there it is, lambda h. Now what is h? It's something that's a realizer for that big conjunction of three components. So the first thing you're going to want to do to get at those components is spread h apart into its 3 bits. So you say, okay, spread h, and then you're going to get, and I tried to name these things mnemonically, you're going to get not and. So that means it's not the case that P and Q. Then you're going to get decidable P and decidable Q. Fairly good mnemonic names, right? So that's what you've got as your components of the hypothesis. You've broken it up into those. And now what do you have to do? You're going to have to produce something that will give you a realizer there. It's going to have to give you an in left or an in right. It's going to have to decide whether it's not P or not Q. So you say, well, okay, the way I can do that probably is to take one of those propositions, either the P or the Q, and decide that. Use the fact that I've got a disjoint union there and I can break it apart. So let's pick P. Doesn't matter, it was the first one. And that's this thing that we were talking about irrelevance in the proof structure, right? You can pick either one of these things. All right, so let's say we decided on dP, and you notice right away a cool thing that in the case when not P is what's true, you've immediately got a witness for the conclusion, because you just take in left of that not P, and you've got your witness. Now you're thinking, well, what should I do in the case when P is true? And if you're just doing this, you say, well, the obvious thing is to now go in and decide Q, break Q up into Q or not Q. When I've got the not Q, boom, I'm done. I put the not Q over there. When I've got Q, you say, oh, this is great. Now I've got P and Q, and I can use the not P and not Q and get false, and from false I can get anything. So that's one way you could have done this second bit. But you might have, and I don't know how you get this intuition, you might have said, maybe there's something easier I can do. I wonder if I need both P and Q to be decidable. You might have asked that question. So you say, well, what if I could I do anything else? Maybe I have enough information already. Oh, what am I doing here? Almost right, only proves it. Yeah. So what am I saying? Is there an easier way than one more case split? Yes. Okay. So how about this kind of evidence for not Q? What we're going to say is one way to get evidence for not Q would be to assume Q is true and then get false, right? So you say, maybe I can do that without knowing anything more about Q. I'm just going to go for that not Q disjunct. Now, so you assume Q. So here we put it into the realizer. Give me a Q. Now you've got both P and Q, and you can go to the first realizer there, which we don't have on the board anymore, but I'm going to explain it. Now you go to not the case, both of them. You put the pair P and Q in, and what do you get? A proof of false. And from that, you can use this any operator to get your proof of not Q. So this is a nicer realizer because it shows you something. What it shows you is you need only one of P and Q to be decidable if you to get that result. You don't need both of those to be decidable. Either one works. Okay, so now we've got our realizer. Can we build the proof from it? Do we have a way of actually building the proof? So here's how we're going to set up the algorithm. We're going to introduce a new kind of turnstile, a semantic turnstile, which says, I'm trying to prove a goal G there from no hypotheses. I'm just trying to prove G. And what I've got is evidence. I've got this realizer. So that's what you have, not a proof, just a realizer. And we're going to try to convert that realizer systematically into a proof. So let's look at the case of G being G1 implies G2, and you've got an evidence term. What do we know about the evidence term? We know something universally true. If that is evidence for G1 implies G2, what do we know about it? So I'll ask you this question. Do we know that it starts with a lambda? No, we don't know that. But do we know that if we compute on it a little bit, if we try to expose what the evidence is, we must get a lambda eventually? That we know. Because if this is evidence for G1 implies G2, in that evidence somewhere, either exposed right away, like we saw in the solution you had, or I have to compute to get it, we are going to have to see a lambda h dot g. So that's pretty cool. That says, all right, you take that evidence term, and maybe you're going to have to work on it, and I'll show you why you have to work on it. But when you do work on it, if it really is evidence, you will get a lambda out of this thing. And once you do, and here we're going to set that up. So we've applied now I already applied the lambda. Why did you do that? Oh, just to speed up things. Yeah, so I showed you the term there was lambda h and then some body, g. So I'm saying, all right, we're going to set it up with h as the hypothesis and now an evidence term for the rest of it. But now I'm going to take this evidence term that you already produced, so we know what it is. It's that spread. Okay, so when you've got that thing, you know what to do. You say, all right, that spreading is going to do the following. It's going to break up those hypotheses just as we expect. So now there they are all typed for you. You can see what those hypotheses are. And we know we're going to have to get a decide on the not P or Q. So for that, the evidence term that you guys agreed with has a decide dp on it. So we again know what to do. All right, let's apply that decide. That's going to break the proof into 2 bits. The bit where we've decided that P is true, so there it is up at the top. We've got a witness now. We've replaced the P or not P by the thing at the very top that says, okay, I'm in the P case. And then you know how to, oh, that's the hard one. Let's go down here, the second one. We're in the, whoops, did I do something wrong there? P. No, I didn't. So I just finished, I finished that proof. Here's the, okay, so I just finished that piece of the proof. So the next one should have the insightful thing. Okay, well, anyway, you would know how to finish this. You can see we're just now typing all the little bits of that evidence term. So you can start to see this as, wow, I'm just going through the evidence term and I'm typing all the bits. So this makes it look like it's not so hard, right? You take the evidence term. But let's, so it's promising. Seems to have worked like a charm. And you should try out the example there for yourselves. I'll put these online. But how about this real simple case? Now we say, let's do something very simple. I want to prove false implies A for any A. So I put lambda f dot any of f there. That's a pretty nice realizer. We can trivially build the proof, and I didn't do that on the previous slide either, did I? No. But you can do that one, trivial, one step. So that looks really good. Everything seems fine until you realize maybe somebody isn't going to give you that nice realizer. They might give you this realizer, lambda f dot 17 for the proof of A. Now, how can they do that? You say, well, you're cheating. That's not a logical realizer, but this is any realizer in type theory. And what you see is if you've got false as a hypothesis, then anything follows. Anything can be evidence for the term. Because now you've got a vacuous hypothesis there. There's no realizer for false. So if there can't be any realizer, then anything, you can show that anything is a realizer, like the number 17, or even worse, like a diverging term. So do you get this? See why this is possible? So there's something screwy going on about the evidence. If you ever get into a position where you've stuck false in as a hypothesis, then you can write down nonsense as your realizer. So this screws up our whole plan, right? We're going to go chugging along here through the realizers, just finding the meaning of it and decomposing. If that was your plan and you wrote an algorithm, somebody would give you this, lambda f dot 17, and your algorithm comes to a grinding halt. And you say, well, I'm sorry, I can't deal with those. And you say, yeah, but that's evidence. That's evidence in my type theory. Yes? Where?
How does that second one work? How does 17 become?
Okay, so I'll do a lambda f and I'll put false in the hypotheses with the name f. But false is a constant term that can't get any realizers, right? So there can't be anything to realize. So when I'm now trying to think semantically about this, that's how I'm thinking. I'm saying there's no realizer for false. Therefore, I have vacuous assumptions. I'm assuming anything goes, essentially, for A. And so I just have to say, I'll put whatever I want there. I have to close the term. I have to put something in there to finish the term. So I could put a diverging term. I could put anything, because you're saying there's no way you're ever going to evaluate that second component. You're never going to use it. And so that's a perfectly legitimate piece of evidence. You say, just throw garbage in there, as long as it's syntactically correct. And semantically, this will be okay, because you're saying there's no way you're ever going to get any kind of input. Your function will have no input. So you'll never be able to use that evidence anywhere in computation. So as a programmer, this is, I think Algol 68 had some weird idea like this in its analysis of its type system. Yeah?
Just discard whatever your adversary gives you and use that.
Yeah, now that's what we thought. I said, okay. All right, this is a problem we can make go away by saying it's never going to matter so much in the proof. You should be able to get rid of these cases. And I was very optimistic about this. In fact, I had an argument that says, look, Perl, we have to put this any term there, and we have to actually build the evidence that gave us the proof of faults, so I should be able to use that. And I worked for a long time on this idea. And it got messy and hard and tedious. And finally, again, it helps to know stuff. I said, well, I remember a really beautiful result by Harvey Friedman that we capitalized on extensively, where Harvey showed you can embed intuitionistic logic uniformly into minimal logic. It was part of his grand scheme for showing something very meaningful. He showed that in intuitionistic arithmetic, you could prove any computable function to be total that you could prove to be total in classical arithmetic, which was a beautiful result, showing that if you're doing computer science, you don't lose anything in terms of proving totality of functions by going to intuitionistic logic. But he ran into this problem. And I was in the audience when he gave the talk on this result. It was at a Kleene symposium. And this theorem, he said, I have a new proof of a theorem of Kreisel, which is the theorem I just mentioned to you. And I knew the theorem of Kreisel. I had taught it to graduate students, and it would usually take a whole day, and nobody ever understood it. So Harvey says, well, let me show you this cute little proof. It takes him less time than I've been talking, for sure. He writes up the proof in about 5 lines, and he says, isn't this cute? I'm going to call it my A transform. And the audience was stunned, like, Harvey, how did you do that? So people asked him afterwards, everybody ran to him, Harvey, how did you think of this? What is this idea? What's the intuition? He says, oh, I don't know, it just came to me. I was thinking and it came to me. It's a nice trick. This is a good thing to say. One of my former students who got his squiggle relation is used everywhere. Doug Howe's squiggle relation. And when people ask Doug, how did you ever think of this? He says, oh, I don't know, it just came to me. So what do people call it? Howe's trick. What do people call this? Harvey's trick, or the A transform. And that's good, because what does it mean? You'd think people wouldn't want this named after him, Howe's trick. Why do they like this name? Because it shows it's elegant, it's cool, it's a trick, it's neat, it's like magic out of the hat. You don't want people to call it Harvey's theorem. They get, oh yeah, he proved it, he went through. You want to know, he found something so cool that it's like a little trick, and out of the hat comes this beautiful result. So this was a trick. But this was a trick that made Tim Griffin and Chet Murty famous, by the way, because Chet used this trick to solve an open problem. And I wish I had time to tell you about this. But he found the first constructive proof of Higmann's lemma. And the story here is probably good. One day, we got a call from Stolzenberg, a mathematician who was visiting Harvard. And he said, do you know this theorem of Harvey Friedman's and Kreisel's that translates between construct? I said, yeah, we know it. He said, well, I think you can use this trick to actually find the first constructive proof of Higmann's lemma, because I've got a nice classical proof that can fit into the Friedman scenario here. So he asked us, would we think about this? So I asked Chet, would you like to think about this problem? Because if you get it, it would be very cool. But the first thing you have to do is formalize Harvey Friedman's whole analysis in New Pearl. He said, oh, that's a piece of cake. He went and he did it. And then he said, okay, now I'll formalize Higmann's lemma and see what happens. But this took him, I don't know, month after month. But every month, Stolzenberg would call us. You got that proof done yet? Did you finish that proof yet? Said, come on, Gabe, it takes months to do this. But finally, we had it. Chet had it. He built, he had to hook 5 computers together into a thing we called ChetNet, and he had all these computers running New Pearl. But one day, he ran in, he said, I've got it, I've got the proof, and we can run it. So we ran it on a trivial example. I won't be able to explain the proof. He runs it, and it works on the trivial example. I said, okay, good. Write up a really interesting example. And he didn't come back the next day, he didn't come back the next day, he didn't come back the next day. I said, well, Chet, what's going on? He said, well, as soon as I tried it on a non-empty list, or a list with 2 elements, I can't get it to converge. So he said, I'm studying the code. I said, well, what's so hard about it? He said, it's 40 megabytes. I said, what? He said, the program is 40 megabytes of code. So we knew, here's a program we knew was correct. It was provably correct. No human could understand the proof, but no human could understand the program either. However, he announced this result, and he got very, he got very famous. There are still probably 100 people working in this area because of this result. All the Minlog guys have jumped on this, and they did the same thing for Kruskal's theorem and other things. And then the French, Hugo Hervelin, who often lectures here, he worked on this problem for another couple of years, and he actually shrunk the proof down to something that was readable. But anyway, that was the first time that you had a computer-verified solution of an open problem in mathematics, but it was so big and so hard to look at that nobody could confirm it really until Hugo straightened it all out. Okay, that's a little comic relief here. Back to the theorem. Okay, so what we can do now is we can use Harvey's trick to map intuitionistic first-order logic into minimal logic. And that saves all the work I was trying to do and your insights there. So you had the right insight. You probably would have done what I did. This is much easier. You say, I'm just going to do it in minimal logic. And in minimal logic, you can't do that example false implies anything. It doesn't work anymore. And in minimal logic, you never get vacuous hypotheses. So that's very cool. And it might be, by the way, I believe you're right, that we could sort out all that complexity. But let me tell you, we got more problems than that. After we got over this one, here's what I thought was going to happen. Say, look, this is starting to look really straightforward. You're set up with hypotheses on one side, a goal on the other, this semantic relation between them, and you've got a piece of evidence. And what are you trying to do? Break that evidence down so you can keep reducing it to something till you get to the axioms. And you look at the options you've got and you say, okay, if the goal is G1 and G2, then I know I'm going to have to get a pair, G1 and G2, and I'll just split this into show G1 is in capital G1, G2 is in capital G2, and go recursively. That looks great. G1 or G2. What's going to happen? The evidence has to be either in left G1, in right G2. For each one of them, you've lowered the complexity of the goal and you've gone to sub-evidence. So again, you recurse. Here, piece of cake. You stick your new hypothesis on the side. You've got a simpler goal, G2. You keep recursing. The same for all. So it's looking really promising now. We just ripped through all the constructor rules and we recursively descend into the evidence term. So this was looking very, very promising. So those are the cases that I just mentioned. The complexity decreases. Now comes what I thought would be another trivial rule. So we said, okay, what about function implication? We've got H, we've got some hypothesis, A implies B, and we've got other hypotheses, H prime. And what we're going to do to solve the goal G is apply F to some term A. And we want to decompose it. We'll say, okay, the F, we know it's in that type A arrows B. The only thing we have to now generate is a proof that A is in A, and then the subproof that I'm not showing here, that from the value we produce, from a B, you can finish G. Now that's smaller. That again goes down. So I thought this would be a piece of cake. All we were trying to argue was, can we guarantee that A is in this type? And then we realized, at least in new Perl, we couldn't guarantee that, because that this element little a, as I mentioned in the first lecture, it might be in a slightly bigger type, and the function will still converge on it. You might have given a function that converges off of A on a bigger set. And maybe that little a doesn't belong to A, but it belongs to something bigger. So this drove us nuts. How are we going to prove this? And then uniformity came to the rescue. We said, well, look, this thing's got to work for any model. What if we could build a model where we had a type A and a function on it such that if you gave that function anything off of A, it would diverge? Then we're golden. Then, as long as you've got one model like that, it rules out doing this for any other model. So we just had to find one model with this property. And unfortunately, that took us a heck of a long time, because we had to bring in our theory of partial functions. We had to say, well, can you use partial functions then in this account? And if you read our paper on the archive, you'll see we have a nice, like, 2.5 pages on things we call retracts that I won't go into. But basically, we did what I told you we would do. We found that you could pick finite types for A and arrange that you would have partial functions around that would diverge off of A. And then we could solve that problem. But this took a long time to figure out. So there is what I'm explaining: finite types, partial models, and that works. Okay, but here's another thing, and I'm going to show you the challenge problem I'm going to have for you at the end deals with this. How do you know when you're applying this function on different arguments that if you ever, maybe you're going to have two arguments that are actually equal, but you can't see this. So you've got to make sure if the function is applied to equal arguments, it's going to give you the same value. And again, this started to drive us a little bonkers, but we realized you can do something really simple here. You can build a model where all the realizers for A implies B are constant functions. All they do is they pick some element of A, and that's all they use. So that's another insight that you have to, and this is again uniformity. We can say, well, among the models are going to be those where the realizers for A implies B is just some witness to B, because after all, you only have to apply that function once. If you see it in a hypothesis, you've got A implies B. You say, well, okay, I need this function only to get B. Once I've got a hold of B, the heck with that function. You could throw it away. So you might as well make it a constant. So it produces just one thing, the guy in B. So that was cool. But again, another trick. But then we realized, oh, for the universal quantifier, this could be bad. Now, that's a function, but you might invoke that function on many elements of the domain. And now, those elements, they're named, like D1, D2, D3. And if you apply F to D1 twice in two different parts of the proof, you better get the same answer. So to deal with this problem, we have to add to the thing we're building up a model of this function, a finite model of it, which is a table that we store with the hypotheses. So that's another little trick, but it's, again, not a hard trick. It just complicates the proof, so that you have to do lookups. When you get to these functions that are universal quantifiers, you have to see, have I used it before, and have I used it before on this argument? Okay, so now, here's the really hard bit. So all this stuff has been predicated on the fact that we're just seeing logical stuff. As we keep evaluating this evidence term, we keep seeing pieces of logic. But the real nightmare is you're going to see some coding of a complex arithmetic argument. Out comes, you're computing on the evidence term, and out comes induction on the natural numbers. So what? What are you doing? And the evidence guy says, oh, I got a cute little proof here using graph theory and number theory, and it uses all this stuff from New Pearl's theory of graphs and numbers and lists. I say, what? That's your evidence? Now this seems really bad. How are you going to deal with all that stuff in the type theory? So what do? What's going to save us in this case? There's only one thing that can save us, right? You know the reflex answer has to be uniformity. How does that save us? The only way you can use the numbers in there is if you actually use constant numbers. If you have, you can't stick the domain of natural numbers in the hypotheses, because that isn't an arbitrary domain. Uniformity knocks that out. You cannot have a hypothesis that says D is the natural numbers. So the only way you can use the numbers is to have built an argument, and I'll give you one at the end as an exercise. And it took us a while to realize this, but when that happens, what do? You just say, well, normalize the stupid term. It's got to give you something. So it'll have to be induction on 17 or induction on 25. It can't be induction on n. If somebody says, I used induction on 25 or on the length of the formula, you say, okay, good, show me what you did. And they do the proof, and you unwind the proof, and at the end, you come out with a piece of logical evidence. That's what you have to have. So for this, we convinced ourselves fairly easily, just when you see those blasted things, normalize them. Now we were really thinking, this is great. So here's a hard exercise. Here's a piece of evidence, a real piece of evidence for that formula up there. This is what you can see in New Pearl. I used an ML-like notation for it, but there it is. That's an evidence term. So you've got H, F, and G. Let N be the greatest common divisor of 10 and 5. In the factorization, finding the least factor of 111. Then let I1 be the iteration of the identity function n times. Let I2 be the iteration of that parent function m times in this term. So that's an evidence term. And if you feed that into our algorithm, what does it do? It normalizes away the GCD, finds that it's 5, plugs that in for n, iterates the function n times. It does a lot of work, but in the end, it comes up with a proof in first-order logic. Okay, now comes the real business. So we finally had the procedure. There it is. Complicated, lots of lines of code, and we wanted to know, how do we know this blasted thing terminates? How do we know on any evidence it's going to terminate? And that argument required something brand new. We couldn't use, Koenig's lemma is classical. If you use that, you can finish the proof. We needed an intuitionistic version of Koenig's lemma, but it was right there in front of us. Fortunately, I'd just taught a course where the students pushed me, the graduate students in logic. They wanted to know more about Brouwer. So they had heard about Brouwer's bar induction. They had heard about the fan theorem. So they made me teach them this. And I had to go back and review Kleeni's book, and it took me, I don't know, weeks to do this. And there they were, logic graduate students who didn't trust Brouwer and were trying to poke holes in everything I taught them. But I learned this. I really knew it. And when this came up, I said, oh my God, that's just the fan theorem. And we could actually add that to New Pearl, no problem. That's classically consistent. When, in fact, Spector found the realizer. And I think you guys who like logical relations, you should actually use that to take Tate's argument and show that Spector's bar induction terms are total. That would be a nice new result. Anyway, we got the result here. What it shows, so here I state that theorem. It says, no, I guess I don't state it. So here's what it says. If you're elaborating a finitely branching tree by a recursive method, and you know that every branch in that tree terminates, which we know because this is evidence, then there's a uniform bound on the running time of the function. So that's Brouwer's it's derived from his bar induction theorem. It's the fan theorem. It contradicts Church's thesis, and that's why people couldn't get this. Remember, Kreisel and Gödel proved that if you had completeness for first-order logic, it would violate Church's thesis. Well, that's why it violates it. You need this fan theorem. So now you can see what was going on there. Okay, so that's the main narrative. We're back to we've got this thing, it really works. Yeah, this is an introduction to the next lecture, actually. So I don't think I have too much time, right? I have, what do I have? 10 minutes? Oh, okay, so 10 minutes. I could tell you a little bit about these partial types. You can see that to do this argument, we needed several ideas that I think only New Pearl's type theory has. I'm not sure, but you needed intersection types, both of binary intersection types and the universal quantifier of intersection of a family. But you also need these partial types. You have to reason about partial functions. And that difference is really pretty cool, because I want to show you what you can get out of these bar types. In addition to the completeness theorem, you get what I think is the world's simplest unsolvability argument. This is the one you want to show your mother about why the halting problem is undecidable. This one you can teach to freshmen. I have taught it, well, not to freshmen, but I've taught it to undergrads. And I'm going to make it a little more sophisticated than you have to. Let me just remind you how we do computability if you've got partial functions. So here's a well-known variant of the 3x plus 1 function. There's a recursive function defined in the usual way. That's called the 3x plus 1 function. And what we know about this is that it converges to 1 on like the first million inputs, but nobody knows whether that's a total function or not. It might actually be partial. So here's how an alternative syntax for it. You could just define it as, well, f is the function like this. Another piece of syntax for it is to use it with a lambda term. And then if you want to use fixed points to do computation, you just write this functional term here where you take f as an argument. And then you can write your recursion as the y combinator or the fixed point combinator applied to this function. And by the way, my colleagues, until last week, or no, last month, I tried every year to get them to take the y combinator out of the New Pearl evaluation system. We actually use the y combinator. That's how we do all of our recursive functions. And I wanted to use this guy, fix. I said, let's just put fix in there. It'll save us 5 characters and all that. They were so happy that we could use the y combinator, they would not take it out. I'm supposed to be like the manager of the project, running the project. I'd say, guys, it's time to take the y combinator out. People think it's silly. They say, no, it's not silly. It is the y combinator. It's the real y combinator. We have to leave it in. So we compromised. Now they put fix in because of some technical reason, a good technical reason. But anyway, here it goes. Now we know how to do recursion in general. You just take the fix of an operator like that. You apply the y combinator to it, and that's how we do all computable functions. Yeah.
Fix is a primitive. It's not defined as
Yeah, we make it a primitive, and we define it the way I'm showing you here. It has
y was also a primitive, or that's defined?
y is defined. It's defined in the Church's lambda. We use Church's, I think. They would know. The people who love the lambda calculus knew exactly which one it was. I wanted it out, so I didn't care which one it was. So here you go. That's recursion. Now, how do you get a non-defined object? If you take fix of the identity function, what do you get? Diverging term, right? So that's our diverging term. That's bottom. Now here comes the simplest argument in the world, that this is all just partial functions. You guys know all this. So here's the way the notation works. We want to type this fix operator. And the way we type it, I had mentioned before, for every type in the theory, like natural numbers, any type, we have a type that we denote A over bar. And those are the terms that, if they converge to something in the type A. So n bar consists of all the numbers, all the terms for numbers that could possibly be partial, could diverge. Yeah?
What is the type for F partial here? Why don't you have to think about A bar to A bar?
Because I want it for the undecidability argument. I'm just, oh, and that's what fix will always do for you, right? Its general type is if you've got a function from A bar to A bar, fix will be in A bar. That's what I said here, right? Where did I say that? I say it here somewhere. Oh, the last sentence on this one? Yeah, there it is. So we rely on that. That's the standard typing of a fix operator. That's what you want it to be. That's what you get. So let me just show. Once you've got all that, here's how you do the undecidability of the halting problem. You say, let's suppose in the theory, for A could be the natural numbers. You could take that, but any partial type. Let's suppose it decides halting, so it maps A bar into the Booleans. Then what we can do is define this number D here to be the fix of a function that, if the H is true of the input, it will diverge. And if H is false of the input, it will be some converging term. This A bar is just something that terminates in A. So think of the natural numbers. A could be 0, then it converges. Okay, so now let's suppose we have that function H that does its job. And what we'll do is we'll take a look at what it is, you know, there's its definition. And let's apply H to D and see what happens. Well, so D is defined this way on the first line. That's the definition of D. So we see that it has the property that if H of D is true, then that function up there is going to diverge. That's what it says in that line. If H of D is false, it's going to converge. So now you can easily argue that H of D can't have either one of those values. It can't be true, because if it's true, it says the thing converges, but it diverges. And if it's false, it says it diverges when it converges. So you can't have this function H. And there's the whole argument. There's no indexing of Turing machines. There's nothing, right? There's hardly anything to this argument. But it's a very strong argument. This argument is not consistent with classical mathematics, right? Because we're saying there is no function in the type theory, in the new Pearl type theory, that can decide the halting of that stupid little fixed point function. There's none. In classical mathematics, that's not true. You just define some non-computable function. You say, well, there's a non-computable function that will decide it. So this result, even though I love it, I think it's incredibly neat, is classically inconsistent. So we don't put it in. We have to separate that part of our theory from the rest of it. And I'm sad about that. But I think we're going to give up on that, because now we're tempted to use more and more results from intuitionistic logic. And this is true in intuitionistic logic. And Brouwer knew it. Brouwer knew. That's why he wasn't so shocked by Gödel's theorem. He said, well, of course there are undecidable problems. So we may talk about that a little more in the last lecture. And now you can forget the exercise. I didn't get there. So I'll state the exercise, maybe this one on the board here, because we didn't even get to talk about record types. But I like to be prepared to go on. I don't want to stop 15 minutes early. Then you'll ask me really hard questions. Okay, so that's it.